idea.
Wait, I think we don't have to include where in the world in the recording.
Okay, well, too late now. Actually, you're right. It's not too late now. All right, so some announcements. Welcome back to winter quarter, to your second quarter of DAV ever. Just a few logistical stuff. We've gotten all of your addresses, so we'll have the parts shipped to you or dropped off to you by the end of this week. Also, thanks to our wonderful president, Brian, we have a new Discord bot, Sparky. So there should be a channel in the Discord called Add Roles, and if you react to the DAV reaction emoticon thing, you should be able to mark your role as a DAV member and be able to see the DAV and be able to just like have a DAV role. And just as a word of good luck with classes and everything else, including DAV this quarter. So with that, on to what are signals, mixed and otherwise? This doesn't hit close to home at all. All right, so signals are basically a way to convey information. So if you're smart, you can not only receive signals and receive them properly, but you'll also be able to understand the signals and know what to do with them and what they mean. So some common signals that we kind of run into as electrical engineers are electrical signals like voltage or current. And then there's also electromagnetic signals like light or radio. But things like sounds, stock prices, and seismic waves can be signals as well if you interpret it that way.
Okay, so now once we know now that we know what signals are, we're going to talk about the Fourier transform. So this is honestly one of the basic concepts behind signal processing. And just before that, we have to review what sinusoids are, of course. And just so we're all on the same page, they come in the form A times cosine 2 pi bt plus c, where A is the amplitude, that's how high or low it goes. B is the frequency, so that's how fast it kind of oscillates, and C is the phase. And the phase is how much left or right is shifted. So obviously the two most common sinusoids that we see these days are cosine and sine, and they're actually the same function but shifted by 90 degrees. So they have a phase difference of 90 degrees. And so once we know about sinusoids, we can talk about the Fourier series, and this is actually thought up by Joseph Fourier. He's a French mathematician, and he came up with the idea that any periodic signal can be expressed as a sum of sinusoids. So basically here, instead of just working with the sinusoid itself, we can instead work with the frequencies. So as you can see here in the picture, we have the sinusoid on the top, and once we kind of think about it in terms of its frequencies, we just have one basically line at whatever frequency that sinusoid is at. And just so we have a better idea of what we're actually doing when we kind of convert it into frequencies. This is an example from Professor Cow's slides. Not me, but shout out to Professor Cow. And so on the left here, we have this time signal of a C major chord. And obviously, it's really, complex, and it's really hard to tell what's happening here. But once we do a Fourier transform on this chord and we look at its frequencies instead of the time information, we can see it's really clear to understand what's happening. There's a frequency at C, at E, and at G. So once we convert into frequencies, it's a lot easier to understand what's going on with this signal. And so the Fourier transform, there's this math equation that you will learn about eventually in EE 102. And all you really need to know about the Fourier transform is that it converts time to frequency. So the input is a time signal, and the output is the Fourier transform in the frequency domain. And obviously there's an inverse Fourier transform as well. You can convert from frequency back into time. So for our purposes, you don't actually really have to know how to calculate this. Like it looks really ugly. There's like integrals and everything, and you're going to learn about it in class. So that's for now. You just need to know that Fourier transform converts time to frequency. And here's this GIF I found. I think it does a really good job of kind of visualizing what's happening. So we have this time signal F in the red, and we can break it down into its component sinusoids, just as with Fourier's idea. And you can see it in the blue. You can see it's the component frequencies of the sinusoids. And now we have all the frequencies at the bottom. And so the top is the time domain signal, and the bottom is the frequency domain signal. And just because I think this is really cool, so we get to watch it again. And again, so red is the time, and blue is the frequencies. And you can see obviously right here, the lowest frequency, it has the highest amplitude, and the higher frequencies have lower amplitudes.
All right, so moving on from that, why would we possibly use the Fourier transform? So obviously we've given you some examples about like looking for from the time domain, we see some like specific frequencies, but is it any more useful for that than that? And the answer is yes. And it's basically because it makes some analyzing and constructing and destructing of signals easier to do. So if you think about this signal right here on the left, this weird kind of wavy signal, this is in the time domain. It seems a little hard to actually work with this signal and see what it's doing if we want to like apply it to some sort of other signal maybe. But if we convert it using the Fourier transform, we actually see that, oh, it's really just this kind of weird rectangle shape. So it's actually just a bunch of sinusoids with frequencies ranging kind of in this range, existing all on top of each other. So that's why the Fourier transform can be useful, because not only might it make time domain signals easier in frequency domain, but if you have maybe a complex frequency domain signal, it could make it easier in the time domain. So here's some intuitive understanding of the Fourier transform, which in some cases is music. So right here you see a beautiful orchestra playing some beautiful music, or me playing some beautiful music. So I could, pull out my violin and say, I'm gonna hit your eardrums at 440 times per second, right? And you'll hear some sort of sound, but that's not really how people understand music. It's not really how we think about music. We don't think, oh yeah, that's 440 hertz, right? So a musical intuition of the Fourier transform is to say that 440 hertz in the time domain that I'm hitting your eardrums at, it's actually just an A. It's a certain frequency we associate with that kind of time wave. So that's kind of your musical intuition behind the Fourier transform.
Okay, up until here, does anyone have any questions about what we just talked about? Basically, the main idea was the Fourier transform goes from time domain into frequency domain. And there's an inverse transform that goes from frequency back into time. Anyone have questions? The sinc function, if you want to go back, it's equal to sine x over x. Actually, this function turns up a lot in signal processing, but not for us. So you don't really have to know it, but it definitely, it looks very, very wavy and weird. So, just transform it and it'll be okay. Okay, if no questions, I guess we're gonna go on to the Fourier transform in real life. And so just now, what we talked about with the Fourier transform, we were integrating over, infinity, and it transforms a continuous time signal into a continuous frequency signal. But in real life, we can't really work with continuous signals because if you have a continuous signal, it means it has infinite samples, and you have infinite data points there, and that means you need infinite storage. So our computers can't handle that. So our solution instead is we take discrete samples of a finite signal, and then we convert it into discrete frequencies. So because now we have discrete samples, discrete frequencies, we don't have the problem where we need infinite storage anymore. And so now we have this formula instead. This is what we call the discrete Fourier transform. And we turn we have the x of small n on the right side, and that n is discrete time, where n is an integer. So basically, instead of having continuous time t, we are working in terms of our samples, which is n. Basically, we have our first sample, second sample, third sample. And so we have the n axis instead of the t axis, and that just is for discrete time. And we also have our big N on the right in the exponent, and that's the duration of the signal. And we get out the k, which is, we get out an x of k, where the k is discrete frequencies. Instead of omega for the Fourier transform, which is continuous frequencies, we have k, which is discrete frequencies, where k is an integer. Yeah, and then so the way we actually get our discrete signals is we do sampling. So actual sensors, so like the microphone we're going to be using, they take samples at a certain sampling frequency. So you run some sort of signal through it, just like my voice or something, and the microphone will take the value at regular intervals. And the time between each interval is what we call the sampling period. And this sampling period ends up becoming like our discrete time. So instead of talking about just continuous time, we just talk about, oh, every period, every sample, what value do we have there? And so the sampling theorem is what we, first we have to talk about the Nyquist interval. And so this is the highest interval that you can sample at without losing information. So basically, if you take your samples too far apart, then you're gonna end up losing information because you can't reconstruct the original signal. And so this formula is t is less than or equal to 1 over 2 times the bandwidth. And the bandwidth is the highest frequency of the signal. And, obviously, the frequency is not going to be very obvious by looking at the time domain signal. So the Fourier transform is really useful for finding what our highest frequency is. For us, for DAV, the FPGA is going to be sampling way faster than we need to worry about. So you don't actually have to worry about being lower than the Nyquist interval. You don't have to worry about losing information. And yeah, so you can see here, this is the picture we had before. And when you go into the Fourier domain, the frequency, so the highest non-zero frequency in that signal is what we call the bandwidth. So here we have the rect, and it's really clear to see what the highest frequency is. It's 1 over t. So that's what we say. That's what we call bandwidth. And what happens when you kind of go above the Nyquist interval? Again, you don't have to worry about this, but you should know what happens. You get aliasing. So what happens is sampling creates copies of the signal, which we eventually kind of isolate. But if you sample too far apart, the copies end up kind of stacking over each other additively. and you get what happens. You get the thing on the bottom where they stack together additively, and you don't actually know like what's where anymore. You don't actually know like which you don't actually know if the start of the signal contributed to that part or the end of the signal contributed to that part, you know? So for example, at like 1/2t, it might be that the start of the signal was 0 and the end of the signal was everything. But you know, since they're adding additively, you can't really isolate that effect anymore. Okay, any questions here? All right, bang.
All right, so moving on. So we talked to you about the continuous Fourier transform and then the discrete Fourier transform. So now we're going to talk about the fast Fourier transform. So what is the fast Fourier transform? So if you kind of go back to this equation for our discrete Fourier transform, you have this big N, and you're taking a sum over big N samples. And for each of those big N's, you're going to be doing an N multiplications of complex values. And so what we find is that we have an order of N squared algorithm for calculating these frequencies. And so this is actually rather inefficient because if you start small with like 4 points, maybe that's not that big of a deal. But as you get larger to more realistic signals, like 128 points, 512, and even into the thousands, you're going to get much, much slower. And you can kind of see how that's significantly different on this order of N squared chart. As you get larger, it just kind of increases drastically how long it'll take. And so what we do is we use kind of an inherent symmetry in this equation to create the fast Fourier transform algorithm, which is order n log n, which you can see is actually a much better algorithm compared to n squared as your signal gets larger. For reference, if you have 100 points, n log n is 7% of n squared. So you can see how quickly it actually gets better. So why do we use the FFT? Well, the FFT is actually, because of its how easily you can calculate a Fourier transform and how it's kind of the quickest algorithm we so far have or commonly use, it's the most universal way to deal with signals. And it works on all finite convergent signals. So it can be like periodic or it can be kind of all over the place. It doesn't matter. We can analyze the frequencies for any signal. And that's basically any real life signal that we hear or see, like it'll start and then it'll stop. So that's why we use the FFT on kind of our audio signals. So the basic fundamental unit for our fast Fourier transform is this butterfly module. And so a butterfly module is essentially like a 2-point fast Fourier transform. You take in 2 points A, B, which would be like 2 points of your audio signal. And then you multiply one by this thing we're going to talk about later called the twiddle factor, which is W. And then you get this formula for A plus W1B and A plus W2B. And so, for example, if you have a 2-point FFT, you'll have the first 2 points X of 0 and X of 1. And what you're going to get out for A plus W1B is big X of 0, so like your first frequency value, and A plus W2B, which is X of 1, which is your second frequency. And so what we find is that because of the n log n recursive algorithm of our fast Fourier transform, we get this butterfly effect in which we just kind of keep combining smaller butterflies into larger butterflies to actually build onto larger FFTs. So in this example, rather than having 2 points, we have 4 points. So just as a kind of a check on your understanding, how many stages does this 4-point fast Fourier transform need? So by stages, we mean like how many steps of butterflies do you go through? Anyone?
So maybe we should explain a little before. So what we're doing with this by stacking these FFTs, these butterflies together, is at first we treat the butterflies as kind of two inputs and two outputs, right? And so, yeah, can you go back to the previous slide?
Yeah.
So here the butterfly has two inputs, which is A and B, and kind of the twiddle factor W, but I guess we can consider B times W as one input, and has two outputs, A plus W1B, A plus W2B. We're going to explain more about what exactly W is later, but just for now, it's two inputs and two outputs. So here for the most, for the base case, I guess, we consider our input signal has two samples, A and B, and our output is our FFT of that 2-point time signal. So we're gonna have 2 points in our frequency signal at the output. Then any questions about the butterfly real quick? Just conceptually, what's happening in this block diagram?
How is W1 splitting? How are W1 and W2 splitting from W?
That's actually my bad. We're gonna explain later again because twiddle factor is kind of weird and spooky, but they're actually different twiddle factors. So like, so the B times W is like B times W1 and B times W2. Okay, so now that we have kind of our base case established, when we have a larger FFT, for example, here, instead of 2 points, we have 4 points in our input time signal. So in our first stage, we treat it as we have two 2-point time signals. So the top butterfly is working on X0 and X2, and the bottom butterfly is working on X1 and X3. And then now we have our outputs. We name them, I guess, Y0, Y1, and Y2, and Y3. And in our next stage, we treat our outputs from the first stage as also as 2-point signals. So what I mean by that is, so the butterfly has two inputs, right? And so for our second stage, our input is going to be Y0 and Y1 together. That is one input. And the other input is Y2 and Y3 together. That's our second input. And then we will basically do the same butterfly thing again. We just run it through the butterflies again. And our outputs from that are big X0, big X1, big X2, big X3. And so at the end of our second stage, that is our completed 4-point FFT. So again, from the first stage, we had four basically. All right. Yeah. All right, Brandon, do you have a better way of explaining this?
Yeah, maybe. So.
All right, I think it might be easier for us to have the pointer as well going through this.
Yes. So we start basically with a recursive algorithm. So like David said, we have first our base case. So ignoring like what the actual like inputs are, you can treat 4 points first as two sets of 2 points, right? And so you're going to take one set and put it through one butterfly and calculate that kind of 2-point FFT, and then do the other set and do another 2-point FFT. And then those 2 points are actually those two separate results are going to work together, and you're going to calculate again. So in this example, we kind of cross these butterflies. So now Y0 and Y2 contribute to make X0 and X2. And then Y1 and y3 contribute to make x1 and x3. And so from that, you kind of get from just like starting small and then getting bigger, you get this kind of recursive algorithm to create a 4-point FFT. Does that kind of make sense? Any kind of questions along that line?
I feel like we might want to sit here and let the thing and just let it like look at it for a while. Again, in the second stage, our input are two inputs. We have two inputs. The first one is y0, y1 together, and our second input is y2, y3 together. Basically, we started from single data samples. So in the first stage, we treat it as 4 single data points. And then once we do one stage of the butterflies, now we have two 2-point samples. Instead of 4 1-point samples, we have 2 2-point samples. And then we go through another stage, and now we have 1 4-point sample. And once we get to 1 4-point sample, that's the end of it. Okay, I'm gonna need some feedback here, if this makes sense or not. Head hurts. Why does it cross so far? That's a good question.
Okay, so it has to do with like essentially what you kind of
Can you
see
draw on
happens.
this too? By any chance?
Can I draw on this?
Is there a pen or something?
I don't think so. I can't tell. I don't think so.
Okay, unfortunate.
No. Okay, so basically the reason it crosses as far, if you kind of, is basically you associate the odd signal values and the even signal values together, I guess, if that's the best way of saying it. So first, you're going to cross these two, which are kind of the even signals, and then here the odd signals. And so then you kind of cross those over again. And it kind of, that's how I don't know, that's the best way I can explain why you need to cross them the way they do.
Let me.
Wait, so y0 and y1 are each like, are all those y's are each like 2-point samples, right? From because x1 or like all the small x's on the left are 1 point themselves, and when you do the FFT with another point, you get the 2-point sample.
So y0 in this case is going to be a plus x0 plus w x2.
Yeah.
And then y1 is x0 plus a different twiddle factor x2.
Sure, yeah.
And the thing what we're saying is that we should consider y0 and y1 basically as one discrete unit.
Yeah, so we look at them together, right?
Yeah.
Okay, yeah. And then we look at x0, the big x0 through big x3 as one unit as well.
Yeah, exactly.
Okay.
So at the start we had x0 is 1 unit, x2 is 1 unit, x1, x3. And once we go through one stage, now we have y0 and y1 as 1 unit, y2, y3 as 1 unit. And once we go through one more stage, we have x0, 1, 2, 3 as one big unit.
Mm-hmm. Yeah, that makes sense. Okay, thanks.
So, I mean, it's hard to be convincing here, I think, because we're not throwing any math at you. but I think the important thing is to build kind of the intuition behind what the butterflies are doing. Just at every stage, we are kind of coalescing the samples together until we get to our final result, which is going to be one big sample. So
Yeah.
1 point, yeah, a 1 point sample, to clarify, that's kind of saying like we have we have our signal and we take like one data point from it. And then we say a 2 point sample is we have our signal and we take like 2 data points from it. And so like 3 point, 4 point, 5 points, like, oh, we have 5 data points from this sample. You know, we waited for 5 samples to happen and we got 5 values from that signal. And now we have these 5 values. So in this case, what would have happened is like we had our, you know, microphone input or whatever, and we waited for 4 samples from the microphone. And now we're running it through these butterflies. And we're trying to convert it into, again, the frequency domain by using the FFT.
And even if you don't really understand the math right now, it could also be easier just to remember, like, this is the idea of the diagram. So if you start from the left and just kind of follow the lines and the arrows, you see like Y0 is made from X0 and X2 and a W2. And then similarly, Y1 is made from X0 and then like X2 times another W, right? And then in your next stage, you have this bigger X. So you can see that X0 is made from Y0 and then Y2 times something. And then X1 is made from Y1 and Y3 times something. And so if you follow those lines, if you draw a butterfly diagram like this and follow those lines, you should never falter with your FFT. If that makes sense.
In the second stage, the reason why it crosses so much, I guess conceptually, you know, Y0, Y1 should be crossed with Y2, Y3, right? But our butterfly, like physically, it only takes in one sample, like 1 point. So even though we are considering Y0, Y1 as a discrete unit, like the butterfly can actually only take either Y0 or Y1. So what's happening in the second stage is we still have 2 butterflies. And one of them is handling like Y0 and one of them is, and both of them are kind of handling the 2, I guess, bits coming in from Y0 and Y1. So now they're working together.
All right, so
And
maybe
one more thing. In this implementation, it's really, it's more efficient with resources because you see in the first stage, we have 2 butterflies, and in the second stage, we have 2 butterflies, right? And let's say the butterfly takes 1 clock cycle to complete. When you're doing the FFT, in the first clock cycle, you'll do the first stage, right? And that requires 2 butterfly units. And the second stage also requires 2 butterfly units. So in the end, you can kind of recycle your butterfly units, but with different inputs. So this takes up much less space on your FPGA because instead of, you know, like 4, 8, 16, however many butterfly units, you can just recycle your butterflies between each stage.
All right, now that we've kind of spent a thorough amount of time explaining this, maybe we can kind of go on to like the general FFT intuition. I feel like, David, you've already explained this a bit, but we can also extend it a bit more if you if you would like.
Yeah. So I guess each stage combines two smaller samples from before and produces a result twice as large. So again, first stage, we have two 1-point samples and we're outputting we have 4 1-point samples and we're outputting two 2-point results. And the second stage, we have 2 2-point samples and we're outputting 1 4-point sample. And again, if you want to kind of extend this logic with 8 samples, we would need 3 stages. And for 16 samples, you need 4 stages. And in your actual implementation, if your sample isn't an exact power of 2, you can just zero pad, so just add zeros to the end of your sample until it fits into a nice power of 2. Okay, any more questions about the butterfly or any of the intuition associated with it? Because again, this is like pretty much like one of the only things you'll be like, this is like the thing that makes up the FFT. So if you don't understand like what's happening with the butterfly unit, it's going to be a lot harder to debug. Okay.
Speak or chat now or forever hold your peace.
Can you like go back to the previous slide so they can kind of like look at it as well?
Yeah.
Yeah. Okay. Yeah. We'll put the answers to these questions in the notes. Okay, go back to the previous one. Okay, so the answers to these questions, there's 2 stages in this FFT. So I guess 2 to the power of 2 equals 4. There's 2 butterfly units as well because there's 2 in the first stage and they're being recycled in the second stage. So 2 butterflies total, and it takes 2 clock cycles to perform this entire FFT. So basically 1 clock cycle for the first stage, 1 clock cycle for the second stage. Again, all the butterflies in a certain stage can run at the same time. So they're running in parallel. Okay, so let's continue then. So the twiddle factor is the W that we were talking about before. And long story short, it's a unit phasor that is rotating about the complex plane, and it multiplies the second input in the butterfly, so the B that we were talking about. And so the way you calculate the twiddle factor, for each stage, it had, so for, I guess, how should I say it? The twiddle factors split the unit circle equally. And in each stage, there's going to be a different number of associated twiddle factors. I know that's really confusing. But so basically for the first stage, you have W2, 0. And you also have W2, 1, not pictured here. But for the first stage, you have 2 possible twiddle factors. In the second stage, you have 4 twiddle factors. Third stage, you have 8, fourth stage, 16, etc. And again, those twiddle factors, they split the unit circle equally. So the first twiddle factor will always have a phase of 0, so it'll always be 1. And then, so for the first stage, there's only 1 other twiddle factor besides the first one, so that one will be at -1.
if you want another kind of intuition about the twiddle factor, it's basically that e to the negative j 2 pi n over n like part. That's basically what the twiddle factor is. And so, and then another intuition about like why there's multiple is like in this first stage, you're just carrying out like a 2-point like butterfly. And then in this next part, you're doing like 4-point butterfly. So you can think of it as like there will be 2 twiddle factors for here and 4 for here. Right. All right.
Okay, and then for your second stage, you have again 4 possible twiddle factors. And one note is you should rotate the twiddle factors in the negative direction, so clockwise. This is just so the math works out. And so again, they split the unit circle equally. So the first one is at angle 0, has value of 1. And the second one, which is W4, 1, because we're starting at 0, is at negative 90 degrees. So it has value negative j. All right, my bad, guys. I made a typo there. Well, let me change that right now. All right, can you represent so it updates the value? Yeah. Okay, so the second one is at negative 90 degrees and has a value of negative j. The third one, it goes to negative 180 degrees with value of negative 1. And then the fourth one is at negative 270 degrees and has value of j. So these are the 4 twiddle factors that are kind of associated with the second stage. 4, it's, 2, the way I remember it is like it's 2 to whatever stage you are. So 2 to the 2 is 4. So you have 4 twiddle factors for the second stage. One note is that the 4 twiddle factors here, they split up the circle evenly. So it makes it so that the first half of the twiddle factors are always negatives of the second half. So you can see, the first twiddle factor is 1, the third one is negative 1, second one is negative j, and the fourth one is j. So, they're negatives of each other. Okay, any questions about actually calculating the twiddle factor? I mean, we kind of listed out the ones you need here. So, if you actually need them, just like go back to the slides, just refer back to the slides.
Any questions up to this point? Because that's basically everything you need to know about like at this point about like how we're going to calculate the FFT. And at this point now we're just going to talk about like our implementation. So
if we only had, oh, sorry, can you hear me?
yeah. Go ahead.
Oh, see, yeah, if we only had 2 stages of, just 2 stages, what would the values of, or the twiddle values be?
So when we talk about
two
stage,
stages,
yeah. So
There you
when
go,
we
you
talk
go.
about stages, we're talking about like this is one stage and this is the second stage, right? So kind of like we said before, in this first stage, we have to consider that there's 2 possible twiddle factors. So like 2 to the first stage is 2 twiddle factors, W20 and W21, not pictured here. And then in this second stage, you have like, you're kind of combining these 4 things together. So you're in the second stage, so 2 to the 2. So there's 4 twiddle factors, which would be like W40, W41, W42, W43, if that makes sense. And so back here we have W40, W41, W42, W43, which is for this second stage right here.
Okay.
Yeah, in your first
Does
stage, you
that
use
answer-
W20 and W21, and your second stage, you use W4. So each stage has I guess, a different set of twiddle factors.
Okay.
So
So what, for example, like W20 and W21, are they like set numbers or are they like variable?
So those are set numbers and they come from this, like we said, e to the negative j 2 pi n over n. So for example, this little 0 is like the little n and the big 4 is the big N. So if you look back here, W40 would kind of be the equivalent of e to the negative j times 2 pi times 0 over 4, which is e to the 0, which is just 1. So that's how we get this. Then W41 is e to the negative j 2 pi over 4, which is e to the negative j pi over 2, which if you remember from Euler, that's just this negative 90 degrees, which is this negative j right here. And then so on and so forth. So they're like constants. Does that make sense?
Yeah, I got you.
Cool. Maybe we didn't explain that well enough, but hopefully that makes sense now. Any other questions before we talk about our implementation? All right. So now we're going to talk about how we're actually going to make our FFT. So one of the most important parts of this FFT is that we are using complex numbers. And so if you go back to our little butterfly unit, we have this part where we do A plus W1B and A plus W2B. So W can be a complex number and B can also be a complex number. So how are we going to do our complex multiplication? So if you remember, complex numbers have two different forms. So you can represent it as like these phasors, like we were talking about with the twiddle factor, r e to the j phi, where r is the magnitude and phi is the angle from 0. Or you can represent it as a plus jb using Euler's identity, where a is the real value and b is the imaginary value. So for our implementation, what we're going to do is that for the twiddle factors and for the points that we input into our butterfly unit, we're going to represent them using 2's complement, like you learned in lab 3, using 32 bits, where the most significant 16 bits will be the real component and the least significant 16 bits will be the imaginary component. And so you're basically kind of implementing this a plus jb representation of it. And then that will make it easier to understand like what the relevant parts of your operations are. And so when you're doing the twiddle factor times b, so the WB part, you're going to be multiplying two 16-bit numbers, which if you remember from lab 3, will kind of result in a 32-bit number. So if you have the real part being a 32-bit number after multiplication and the complex part being a 32-bit number after multiplication, you kind of result in this 64 bits for the real and imaginary parts together. But now when you do a plus WB, right? A will still be 32 bits, but W1B will be 64 bits. So how are we going to fix that? And what we're going to actually do is we're going to truncate the products of both the real and imaginary parts to be 32 bits. And so you're basically going to work with the upper 16 bits of both the real result of multiplication and the complex result of multiplication and do sign extensions as necessary. And then one other note about when you're doing your multiplication is that you actually end up with 2 repetitive sign bits. So rather than like the most significant 16 bits, you can actually start from 1 back. So rather than like say 31 to 26, you can do like 30 to 25 hypothetically when you get your result. Or I guess in this case, instead of 64 to 32, it'd be, or 64 to 48, it'd be 63 to 47. Does that make sense? And so another thing is that, like we said before, here we have 4 twiddle factors, but in reality, the first 2 are actually the negatives of the latter 2. And so you can actually use only half of the twiddle factors. So now we kind of have this full image of a butterfly unit here. So rather than doing thinking about it as two separate twiddle factors, you can think of this as one twiddle factor. And then this one, rather than a separate twiddle factor, you just subtract it. So like x0 plus W20 times x2, and then x0 minus x2 times W20. And then similarly for here, rather than thinking of W40, W41, W42, W43, you can do W40. So you do that plus W40, that minus W40, and then this plus W41, this minus W41.
Okay, so because the main idea of the slide is you have to multiply your twiddle factor by 2 to the 15th, which is left shifting by 15, or as much as you can within the limits of with whatever size you declared your register to be. And the reason for this is basically when we truncated our product earlier from 64 to 32, we did a right shift by 15 because we took the upper 16 bits of our real and imaginary, whereas before there were 32. And so that means we basically shifted that part to the right. And now to make up for it, we need to shift our twiddle factor back to the left. And this is gonna give us the right magnitudes. And so our practical butterfly unit, this is the butterfly unit that is probably gonna be easier to actually implement because the twiddle factors, they're negatives of each other. You can actually just replace the bottom addition with a subtraction, and that will eliminate the need for you to have a different W1 and W2 in one butterfly unit. Now you can just input one single twiddle factor and it'll work for both of them. It'll work for both outputs. So here, your two inputs are going to be A and B times W, and your outputs are going to be A plus WB and A minus WB. And again, the stages, we talked about this before, but the important thing about the FFT is you get to reuse the butterfly units. So that means that each stage, each butterfly is doing a different thing, and it's going to get different inputs, and the outputs have to go to the outputs will end up somewhere different. So besides just writing the butterfly units and just initializing them and figuring out your twiddle factors, you also need to control what stage the FFT is currently at, and you also need logic to control what each butterfly is doing at every stage. So what inputs it's getting and where its outputs are going. This is similar to pipelining in the sense that you need to make sure your inputs and outputs are being synchronized across each stage. You know, you're not leaving any operation behind. Okay, up till here, any questions about why we're doing any of these kind of tricks with the implementation? Okay.
All right, with that being said, we have lab 4 for you. We understand that this was probably a little bit of a confusing lecture, and honestly, this is probably going to be the most complex part of building DAV. So we're giving you lots of time. And so we've kind of broke it down into 3 checkpoints. The first 2 checkpoints will be due Sunday of week 3, and the last checkpoint will be due Sunday of week 5. And we're gonna have you start off small by implementing a 4-point FFT processor in Verilog. So that way you just kind of understand the intuition behind the system, why the math works, and why how we can kind of build this system together. So, and now that we have put you with your teams, hopefully, and we've created group chats for all of you, hopefully you've also created group chats with your teams, just your teams. And so hopefully you've had a lot of contact with them and you'll be working with your teams for this project. And so you can kind of refer to each other when you need help. But also if all of you are confused, don't worry, you can ask us as well. So with that being said,
we're also going to release some more kind of supplementary materials to kind of walk you through the process as well. So, I mean, it's kind of a lot to like explain the FFT off like a static image on like a PowerPoint presentation. So hopefully like whatever we release is going to make it a little more clear. Like I understand, like it's kind of a lot to like basically run through E113 in one lecture, but we're trying to make it as smooth as possible.
And we're not only gonna like have our own resources that we're giving you, but also like there's the internet. So you can probably find other supplemental material on the internet if you're a little confused. But with that being said, that's the end of this lecture. We'll be releasing Lab 4 and our supplementary material as soon as possible, so that way you guys can get a head start on it. And yeah, if there's any questions, we'll hang around a bit